Good morning to one and all. I am Parthiban working as assistant professor in the Department of ECE, Sri Muthukumaran Institute of Technology, Mangadu, Chennai. Now I am going to talk about the subject called electron devices, which is coming under the regulation R 2025. The subject code is EC25C01. Particularly, it is meant for second semester ECE students. Now I am going to talk about the topic called the generation mechanisms as well as about the recombination mechanisms, which is prevailing in the semiconductors. The first generation mechanism is called band to band generation, which is also known as direct generation. In semiconductors, the electron normally occupy the valence band, which is also lower than the energy band. When sufficient energy is supplied, an electron can jump from the valence band to the conduction band. This energy can be supplied in two ways. One by means of thermal energy. The second, it can be from optical energy, that is the source is light. When the electron moves to the conduction band, it leaves behind a hole in the valence band. This creates an electron hole pair. This process increases the number of free electron charge carriers. This mechanism is very important since it determines the intrinsic carrier concentration. It helps in conduction of current. It forms basis for photonic devices. For example, in silicon at room temperature, the thermal energy is continually generating the electron hole pairs. This is the simplest and most fundamental generation mechanism that we can have. So, in the next slide, we are going to see how about the recombination generation, center generation types with two steps together. In practical semiconductors, there will be defects and impurities that always be present. So this will act as the trap levels. The carrier generation can occur through these traps. The process that is occurs in two traps, one, an electron from the valence band moves to the trap level, then trapped electron gains energy and moves to the conduction band. As a result, also whole electron pair is generated. This mechanism is called trap assisted generation mechanism. So this process is slower than that of band to band generation because it is very important. It is due to the defects in the semiconductor. So it affects the higher combination rate. It lowers the efficiency. It helps to have a very poor device performance. So the manufacturing aim is to avoid as much as possible. Next, we can have the generation method that is called impact ionization method. So impact ionization is one when a strong electric field is applied to the semiconductor. Under the influence of high electric field, the electrons accelerate and gain higher potential and kinetic energy. So when a high energy electron collides with an atom, it can break a covalent bond. This releases a new electron pair. The newly generated carriers can also gain energy and create more carriers. This leads to a multiplication effect that is called avalanche multiplication effect. So this avalanche multiplication principle is used in the photodiodes as well as in high voltage devices. However, excessive impact ionization can cause a device breakdown also. So the next we are going to see about the photo generation. So the photo generation occurs when the light energy generates the charge carriers. When light falls on a semiconductor, the photons transfer energy to the electrons. So the photon energy is greater than that of band gap energy. The electron moves from the valence band to the conduction band. So this creates an electron hole pair. So this generation rate depends directly on the light intensity, the absorption coefficient, the material properties. So this is the operating principle for the solar cell as well as photodiodes as well as for optical sensors. For example, in solar cells, the light or sunlight energy generates the carriers that produce the current. The photo generation converts the light energy into electrical energy. Coming on to the next slide, which shows the important nomenclature. So nomenclature is nothing but the structure. So the structure of carrier concentration at equilibrium. The electron concentration is represented as N0. The whole concentration is represented as P0. When the external energy such as light or voltage is applied, additional carriers are generated. These are called excess carriers. The excess electron concentration is represented as delta N. The excess hole concentration is represented as delta P. The total electron concentration becomes N equals N naught plus del N. The total hole concentration becomes P equals P naught plus del P. So this condition is called non-equilibrium condition. This concept is very important in device analysis. Then coming on to the SRH capture and emission. So SRH is nothing but the Shockley-Reed-Hall recombination, which is occurs through the defect level. There are two main processes that we'll have. One is called electron capture, the other one is called electron emission. In electron capture, an electron from the conduction band falls into the trap level. In the electron emission, a trapped electron gains energy and returns to the conduction band. This process determines the recombination rate. This mechanism is dominant in defective semiconductors. It reduces the carrier lifetime. So the SRH recombination and generation is a very important one in the semiconductor physics. So the trap centers can cause both recombination as well as generation. The recombination occurs when the electron and holes meet and annihilate. The generation occurs when carriers are created through trap levels. The balance between the generation and recombination determines the carrier concentration. This directly affects the device operation. For example, higher recombination reduces the current in solar cells. Therefore, controlling a recombination is a very important one. Then we coming on to the next topic, that is called recombination a lifetime. It is the combination of all the three recombination process, namely the Shockley-Reed-Hall recombination process, the radiative recombination process, and the third one, that is called Auger recombination process. The total lifetime is influenced by all the three mechanisms together. The carrier lifetime depends on the, first of all, the device speed, the device efficiency, device performance. Higher lifetime improves the device efficiency. Then coming on to the surface recombination that occurs at the semiconductor surfaces. The surface atoms have broken bonds. These broken bonds act as the traps. They increases the recombination rate. The surface recombination reduces the carrier concentration. This reduces the device efficiency. The surface passivation is used to reduce the recombination, which is very much important in the solar cells. Coming on to the next topic, how the surface recombination velocity works. So it measures the recombination rate at the surface. Higher velocity means higher recombination. Lower velocity means better performance. So engineers use surface passivation techniques to reduce the recombination velocity. This improves the device performance. Photoluminescence is used to study the semiconductor physics. So the properties are very important. When the light excites the electron, the recombination emits the light. By studying the emitted light, we can determine the material quality, the defects as well as impurities also. The photoluminescence is used for semiconductor testing. So with that, I am winding up my lecture. These are the references that I made. Thanking you one and all for hearing my lecture. Once again, thanking you one and all.